Hello, everybody. I will now speak on the topic of thermal management system design for battery electric vehicles. Does everybody hear me okay?
Yes, we can hear you, Martin. Thank you.
Thank you very much. I can start with saying that, in essence, all models are wrong. There is no perfect model. There is no model detailed enough that it captures everything in reality. And on the other hand, some are useful, as George Box said in 1979. And this is not all bad, because a simple model purposely built not to contain everything is often more than its accuracy and level of detail. It's often more than enough, and it often beats a very detailed and complex model, not least when you're debugging it, because trying to calibrate it to data, you will find yourself with the huge model will take days and weeks to calibrate, whereas a simple model will not reach the same level of accuracy, but it's much more nimble, it's faster, and you can work it more. And I'll come back to that. So why does this even matter? Well, I work with thermal systems for battery electric vehicles, of the larger kind, but this is applicable to most vehicles that have a thermal system, or even you can extend it to any thermal system, or actually any system, but I focus on the thermal kind. Also for maybe a building or a vehicle that's not running on the ground. This could be for aircraft thermal systems, ships, what have you. Doesn't really matter. Modern systems for battery electric vehicles often include heat pumps to save on battery energy. We want to recycle residual heat from various components. For example, the drivetrain contains a lot of heat that we can reuse on a cold day to heat the cabin via the heat pump. So these systems function in a multitude of modes, depending on if it's hot outside, if it's moderate hot, very hot, cold, super cold, around this freezing point, and what do I do with my vehicle? Do I have a heavy load? I'm driving uphill, downhill, so on. So they have to do a lot of things, and as such, they contain a lot of stuff. For example, the system I'm just working on has 7 valves, 4 pumps, 1 electrical fan, 1 heat pump, 1 electrical heater, and the different combinations of settings for all these components, which are 14 in this example. There are so many. You see a small sample on the screen just to show you that this is a lot. We really can't do everything like manually. We can't control the system manually. So how do we decide when to use what settings, and how are things ever going to be optimal or optimally operated to preserve as much energy in our battery system as possible? Well, it's no mean feat, because even though it's a simple, we pump around coolant, glycol and water combination in hoses and pipes using standard turbo machinery pumps. The combinations, the sheer number of combinations in the system for their operation, it's enormous. So we have some examples on the screen, which I happily stole from the internet, because if they're public on the internet, I could share them. I thought you have the references there. Here's the Tesla Model 3. This is something from the Schaeffler Group, automotive sub-supplier, on the screen, and this is from a paper. You can see it here if you're interested in it. I didn't read the paper, I just nicked the picture. But you can see here that we have an HVAC unit with a positive temperature coefficient electric heater. We have a blower, we have valves, we have pumps, we have high voltage batteries, we have the powertrain, we have another pump, we have a chiller, fan. There's a lot of stuff, and how to operate these simultaneously, it's a huge question. So what to do? Well, if you look at all these details at once, you quickly become very lost very quickly. One solution is to segment the model buildup, meaning you have different levels of details in your model for different project tasks or phases, meaning, oh, I don't build a model of this particular thermal system for this particular vehicle. I build a family of models which I use, and I use different members of this family for different tasks. Usually the simpler models early when you have more concepts to develop. Another complementary approach is also to work with large experiment matrices, meaning I use my model's simplicity and speed to my advantage. And then I spiral back. So meaning instead of, as management theory always goes, is our development is linear, and then you start with a wide range here, wide scope, and then you go on here. Actually, you do spiral back a lot. You define your things, you design it, you test it virtually or in a test rig, and then you go on and take your feedback, you define it again, and then so you spiral back and you see that you actually move backwards in some respects. So there's one logical line going this way, in that logic or in that space, you actually move backwards, but at the same time you move forward along the spiral, which is in another dimension if you want. So you actually move forward along these lines, but in some respects you actually go back. So you can back from my more detailed models. Oh, I have to go back because my test showed me I have to redefine. And then I move along, and then I test again, and see then now you move further along according to both dimensions. So this is how I like to think, that it's no disaster, or it's not a bad thing to actually move backwards in your simulation hierarchy. So how did we do it? Well, we created 2 new fluid libraries because I work with thermal systems. It's a lot of fluids, coolant, liquid, and air, incompressible air in this case. So we don't have to do any fancy stuff for incompressible or for compressible flow, high Mach number fluids. We created 2 libraries. We decided to call them thermofluid and flow. The names are almost arbitrary. We created them from scratch. We had a new interface definition. We created new media models based on the structure that we wanted. I will show you some examples. We created a full set of components. And as a design principle for these libraries, we use limited extents in modality. You can extend forever if you want, but we'd have limited extents, and we don't use very many partial models, which goes contrary to the software engineers thing that you should reuse and make maintenance easy and bug fixes only in one place and so on. Since not everybody will be expert users, we created these models from the perspective of ease of understanding and ease of reviewing, rather than so if we introduce a bug, it's possible using this approach it will actually be in multiple places, but most of the code is very similar in each component, so it should be easy to find. But we do that because having an overview of almost the complete model at once actually also helps debugging and introduction to Modelica and ease of understanding, introduction to this library. So that's why we chose that as a guiding principle when we wrote the libraries. We created everything you see on screen. We created components for, and we created icons and everything from scratch. So the connector we did in the flow library, the thermofluid, I will not show because it's almost duplicate. The difference between the 2 libraries, if I move back, is that this deals with energy balances, heat flows and energy flows, but does not do any hydraulic calculations. If you're interested in pressure drop and flow balances and stuff, you will have to use this. In this library, which is used for conceptual development, you will have to, in each branch of the system, define your flow, volume flow or mass flow, it's your choice, explicitly. So I use this a lot for concept development, but then when I design my system, I go to this one. I will come back to this eventually. So we had a fluid port. You have to have a flow variable, which shows mass flow. We have a potential variable. Pressure is an obvious choice in fluid systems. We have two stream variables. We use enthalpy and we use a mass fraction x. But in all practicality, you can use x. X can be almost whatever, depending on how you write your media model. The media model is written according to this principle. We created first a template, and all functions have a name like property, underscore, and these are the input variables. And for the flow library, we take pressure, temperature, and the variable x as input. If we use them or not, that's really not the question here. That's what each function needs to work. And then we create a template, and then we extend that template. And for liquids, we typically populate it directly with equations for the fluid properties. In our case, different versions of ethylene glycol. Some of them are hard-coded, doesn't use X because they're hard-coded for certain glycol concentrations. Some have X as an input, and then you can vary very easily without changing the media. You can vary the glycol concentration. For ideal gases, we did a little different approach because a lot of gases you can use the same set of state equations and just change the coefficients. For example, when you define viscosity, you use Sutherland's law, and they have the same type of coefficients regardless of the gas, if it's nitrogen or air or hydrogen, for example. Same thing with if you use a variable Cp, you can use the NASA-Glenn coefficients, often called the Berkeley coefficients or polynomials. You can download a set of those for many different gases from the web and implement that. So that's how we did it for gases. It's just more practical because those libraries are already there. It doesn't really exist for different coolants. So there we implement them directly. Then we build a conceptual model. The example shown here is not really, it's a lot simplified from what we would have in a vehicle, because here we have a radiator in the simplified thermal fluid library, which is yellow. I call it the yellow library. We don't have a pressure drop or anything, so we don't have a fan to drive the flow through the radiator, so that's explicitly input. We have a sub-circuit here for something we can say it's the battery. Have a heat pump or a refrigeration system with a refrigerant. Not modeled, we model its behavior, not its internals. Then we have two branches of coolant going to the drivetrain, my little drivetrain model. One for the gearbox and one for the motor inverter combination. And then this little drivetrain pushes on our vehicle model, and then some controls into that. And then, yeah, we can drive this. We can define a drive profile here so we can drive from A to B. As it happens, I'll show you some results later. So this is the library where I mentioned we have energy balances and heat flow only. We would have to, you can see here, I put in my pump icon. I actually put in explicitly what my mass flow should be, and also in the sub-circuit here. And then I explicitly define in this, I use a valve icon, but it's actually a flow splitter telling 0.7, the fraction 0.7 of this flow here goes in this branch, and then 30% goes here. I explicitly define that in this library. Oh, what happened? Okay, back again. Not sure what happened there. So I typically use this library and this type of detail in models to evaluate many concepts, and this can be used to create a first conceptual design of a control system. This conceptual model I ran in a drive cycle, because I have a drivetrain and a vehicle model, so I can evaluate in a drive cycle. It does require that I first created a conceptual control system, because otherwise my thermal system won't work. Without the control system, it will work in manual mode or steady state modes only. So before we actually do the drive cycle, we create a large test matrix with thousands of points, and then we do something called a system characterization, or I create data and hand it over to my control system team members, who use that to perform a system characterization, often using Simulink, who has tools for this, and I in Modelica. And then from that, they define a control system. They define the system from the control system point of view, or we decide to do a hybrid approach and maybe use this data to train an ML algorithm. We did show in an advanced engineering program last year together with Wolfram that it was possible actually to train with using data from these models exclusively to train an ML without any different control functions, just an ML algorithm, a neural net created in Mathematica, to control one of these systems over a 4-hour drive cycle in for various times of the year, meaning different ambient temperatures. And then once we've done that, we model the system again using the other library, the flow library, where I showed you the connector and the media model. And we include hydraulics. So this allows us to actually design the hydraulic circuit. We can select component. We can use this as a guide in selecting components. Pumps, fans, we can size the heat pump, hose and pipe diameters and lengths. We design the system hydraulically. And at the same time, we continue with the next step in the control system development, because at this stage, we add more functionality, we add more detail, so the control system designs need to be fine-tuned. Once we have rig testing, meaning data from the real world, can be scary, but we use that data to calibrate these models to see that our pressure losses and flow balances are correct, our thermal masses are adequately represented, and then we can calibrate the control system again. And the reason we do that in steps is that typically, historically, you would design your system, then you would design your control system as a side activity. These come together first time in the vehicle, and then you spend months calibrating and fixing things on the software in the vehicle, which is very expensive and also not very practical, because you only have the vehicle very late in the development process. So now we can do it years before we actually have a vehicle, to find bugs and things we haven't thought of, which we always do early. So to wrap things up, to provide a couple of minutes for questions. No model is perfect. So we utilize a stepwise approach, a tiered approach if you want, where we add detail as we go along and as we go back and forth. You can see it as a pendulum or as a spiral in my view. To down select concepts, we run huge DOEs, tens of thousands of cases. We haven't really gotten to the tens of thousands yet, but maybe 1,000 is where we've gotten so far. We're developing a new workflow as well. To do system characterization, train algorithms, or something else. And we add detail as we go. And then we start all over. Thank you very much.